So all the numbers you saw so far were for the drive managed SMR drives. However, we also wanted to know what the performance was for the host managed SMR drives. As you saw in the previous slide, the characteristics of the drives are different. And in the host managed drive in particular, all the burden of managing the drive and doing optimizations relies on the user or the operating system. One thing John did not mention is that each of those zones that we had in the SMR drive actually have a pointer where you are going to go to make your writes. In the case of the drive managed drive, it's the drive itself who's managing all of that. But for the host managed drive, it's your responsibility to go ahead and write only starting at that point. If you're going to try to write anywhere else, the drive will reject your request for the write. So what it is doing is the disk is transferring all the burden of all this management to the user level or operating system or file system level itself. The good thing about this, however, is that now the performance becomes much more predictable because you are responsible for it. So ideally, we will test the host managed drives with Swift itself. We'll just switch the disks and do the same test that John ran. However, that's not possible because now we need to do lots of things ourselves. And Swift is doing much more. Swift is doing operations on reads and writes, of course, on directories, on symbolic links, and metadata on the files. If we were to go ahead and implement all of that for the host managed SMR drive, we would be getting very close to some sort of user level file system. However, we really care about the performance for the reads and writes. So for that purpose, we wrote a simulator that will drive writes and reads and read writes in specific ratios to try to understand what are the performance characteristics of these drives. So as you can see here, we have a simulator section that we can configure to do reads and writes in any ratio we want. They send all the requests to a processing module. This module, what it does is, for the reads themselves, they will call directly to the drive libraries to make the read. For the writes, it's going to use some internal buffer that we configure between 2 and 4 zones in size. And when those buffers are complete, there's one part of the process that is actually doing the write to the drive, therefore optimizing the writing on the drive as much as we can. At the same time, you will see on the right side, there's the fragmentation process. So due to the sequential nature of the writing of the zones, one thing that may happen over time is that you will not only be writing files, right? At some point, you're going to delete some of them. And that will leave you with fragmented zones. And you don't want that. What you really want is to have things as compact as possible. So this fragmentation process, what it's doing is reading from the beginning of the drive, compacting all the data, removing all those holes that you have in there, and writing them at the end of the drive. And it's running at the same time as we are doing all these other operations. As you see here, all of these operations are going through a set of libraries. Those are called ZVC libraries, which come from the manufacturer of the host managed SMR drives. So we're not calling the drive directly, we're calling the drive through these libraries. So these are the absolute numbers that we get for writes, for reads, and for write-heavy read writes on the host managed SMR drives. Our intention here is to try to see what is the best that we can get from these drives, but not under the best possible situations. So we are dealing here with very small objects, which are somewhat detrimental to all the reads, because it's forcing the drive to go and read very small chunks of data all the time. Let's start with the writes, which are at the top. The numbers that we get are fairly stable and very close to the rated write speed of the drive. Now, when we begin to disturb these writes a little bit with the reads, of course, we will see the performance degrade a little bit, because after writing a certain amount of data, we're going to introduce a few random reads there, which are going to take the head all over the disk, and then we're going to continue to the writes. The intention of that is to see a somewhat more normal usage of the drive under these scenarios. And at the bottom, do you see the reads? And the reads are performing fairly flat, and this will become important in the following slides. But one thing that we learned from the manufacturer here that is very important at this point is that the libraries that handle the drives, they don't do any caching or any prefetching at all. So for every read operation that we are doing, we are actually issuing a SCSI command, making the disk respond to that, bringing it back all the way up to the application, and then continue. The disk is not trying, the libraries are not trying to be smart and read more than one track and more information as the operating system will. Therefore, the consequences of that is that with this testing scenario, the reads do not scale. But it's not only about the host-managed SMR drives. We also want to compare with the PMR drives, because we have something running today. We want to know how does it compare with this new technology. So we did a read-writes and read-writes comparison between these two types of drives. What we can see here in this chart is the performance results for the reads. So the red line that you can see, the one at the top, is the performance with the PMR drives in what we call no direct access. So I need to point out what we're testing here is the same simulator that we had before, but running on the SMR drive and on the PMR drives, simulating SMR drives. And there are two ways in which we can do that. We can make the access to the PMR drive as any application will, trying to use all the optimizations of the operating system, that means caching and prefetching as well. Or we can do a direct access to the disk, which is much more closely to what the libraries in the SMR drive are doing, right? So we wanted to do this comparison. We see the performance with a PMR drive, what we call no direct access, which is using all the prefetching, using all the caching, scaling very well up to roughly 45 simultaneous processes. Then we see the middle line, that's the SMR drive, that scales fairly close to the PMR drive up to about 10 processes, and it flattens out from there. And the reason for that is what I mentioned before, that these libraries are not doing any caching or prefetching at all. So it's reasonable for them to scale up to a point and then flatten out, because you can really perform any better than that. At the bottom, you will see what we call a direct access to the PMR drive. And what this is doing is disabling, we're purposely disabling all the caching, all the caching being done by the operating system when accessing the drive. And you can see this is very flat here. And the reason for that, and we learned this recently actually, is that this is being purposely protected by the mutex on all the operations, and is being done at the level of the libraries themselves. So what's happening is this is not going to scale at all. So unfortunately, that's showing a somewhat artificial way in which they are protecting all these operations. So it's not a fair comparison with a direct access to the drive, unfortunately. So these are performance numbers for the write. What we can see for both the PMR drive and the SMR drive is that both are performing the writes very close to the rated specifications of the drives. Clearly, we will see that when we're doing direct access to the PMR drive, it will lower its performance, right? But all of them stay within certain parameters. And the one thing that we like to point out is how flat the SMR drive is. It's fairly constant, and it's very, as I said before, it's very close to the rated performance for the drive. And finally, we want to do the read-write comparison. And notice here that the moment we begin to interrupt the writes on the disk with some read operations, we can see both the PMR and the SMR drive performing fairly close. So some conclusions that we need to get from all the slides that I just showed you. First, we're dealing with the first version of these drives and the libraries themselves. They did not do any caching so far because this was the easiest and the simplest implementation that they thought they could have right now. They're leaving all that burden for the moment to the user, though I'm pretty sure there are lots of opportunities for improvements in those libraries with respect to caching. And the other thing that we see is that there's a very clear compromise that you may want to have here, right? We're talking about what performance versus what density do you want to have, right? It's either one or the other, clearly. And there's potential for having very good data density in these drives as well. However, as we can see here, under write-heavy read-write scenario, we can see that it's performing fairly close.